Actually, let's start recording. Yeah, let's just put this disclaimer, smaller beta wins the race. Okay. Okay, I'll keep this problem for dessert then. Or maybe, okay, maybe let me give you this problem and then we'll see. The others will be required to look at it as well.
Wait, can you simulate the egg race with like a cylinder rolling inside of a larger hollow cylinder?
It's a good question. You're thinking in the right direction.
And they have like the same, like the small cylinder rolls without slipping inside of the larger cylinder, which rolls without slipping inside on the ramp.
Ah, yeah. So you'll have to grease them pretty well, yeah, to imitate the egg content. Yeah, if you do that, I think it's a decent model. But do the testing.
Wait, does it?
The yolk, yes, but the white and so it's filled with some kind of liquid.
Wait, does
You can imitate that by I'm not sure if the yeah, if you don't want to waste eggs and you happen to have, say, soda cans or something, that may be a good replacement. Okay, but let me still give you that problem that I prepared. So this is really not anything recent we discussed, but I think it's pretty insightful. Hey, Abhijit, welcome.
For being there.
Perfect timing. So this is the thinking problem that I wanted you guys to look at. So Alice and Bob want to determine the spring constant of a given spring. They decide to suspend a block of known mass m from the spring and measure the stretch x. So in the figure, you see the setup. This is the relaxed spring over here, and this is the equilibrium position of the block. But they take two different approaches to how to compute the k. So Alice just said, oh, I'm going to use Newton's second law for this equilibrium. The forces cancel each other, the magnitudes are equal, so mg equals kx, and when you do the algebra, you get that k equals mg over f. Okay, Bob decides to use the energy approach. So long story short, he equates the potential gravitational energy and spring potential energy, and when you solve this for k, you get the same answer but times 2. So both of these can't be right. So Elvin, what do you mean missing k?
It's missing kinetic energy because like when you let it just fall, then there's kinetic energy because it oscillates.
Okay. What about what if you just lower the block with like 0 kinetic energy?
Wouldn't there still be like small oscillations?
You can make it arbitrarily negligible. So Joseph Fabjet, what's your take on this?
I don't know.
I mean, do you have a gut feeling as to who is correct?
Oh, would there be like more energy on the other side of this spring as well?
What do you mean?
Like the wall exerts a force on the spring as well
Okay.
when you stretch it. So
Oh, you don't really stretch it because, I mean, it's being stretched under the influence of the box. Okay, well, let me tell you how this problem came up. It was a while ago. It was a physics TA meeting at university, like at the main campus, prepping for a lab, and this question came up. It was like a dozen, if not more, physics grad students, and they had hard time figuring this out. Hope that helps. Um, yeah, if you guys don't get it in like 2 minutes, we'll probably put it on the homework set.
I think it's Bob, but I don't know.
I mean, Bob is correct.
Yeah.
So if you think that Bob is correct, you need to find the flaw in Alice's argument,
Okay.
and vice versa. Or maybe they're both wrong.
well, is it that like the initial, like it should be mgx is equal to the change in kinetic energy and not just the kinetic energy itself? So then it should be like mg delta x is equal to half kx f squared minus half kxi squared.
Yeah, that's fine. So let's write it. So you're saying mgx equals what?
Equals to half kxf, yeah. This is delta k, basically, minus half kxi squared.
Yeah, but x initial is 0. It's originally relaxed. So the stretch
So
was
that
0.
would be at the end. So it's correct.
Yeah, so yeah, this part is fine. So that means
Yeah, that's x away from equilibrium. So isn't that right?
Say it again. Yeah, so this is relaxed position. X is 0. At the end, it's stretched.
Well, but it still has some energy in it because it's stretching under its own weight. So the energy isn't like 0 in the beginning.
You hold it. You hold it in the beginning at x equals 0. And you just lower it so that kinetic energy
Do you lower
doesn't
it?
get involved.
Like,
Yeah.
or does it lower itself? Like you just let go, right?
Well, if you let it go, that would be what Elvin described. If you let it go, there is kinetic energy involved. I don't want that, so I just lower it with like essentially 0 speed. Joseph, any thoughts?
I can't figure out which one the flaw in either of the arguments.
Mm-hmm. Okay.
Wait,
So
is it on the right path to say that like the x's in the two are different?
well, it's the same thing. So you can say that this is the 0 level of potential, gravitational potential energy. Then x is indeed the height that
Well, then
contributes
if
to.
you're lowering it yourself, then wouldn't the flaw in the second one be that you're using kinetic energy? Oh wait, no, that's elastic energy. Oh.
Yeah, so the whole point of your gradually lowering it is that you kill kinetic energy. Okay, I see that it's not an easy problem, so I leave it for you guys to think about. Oh, and Abhijit, in the beginning, we discussed the current homework that got posted yesterday, and you, I think Wednesday night. Just wanted to touch base and see if you have any issues, if you know how to approach each problem. If you haven't looked at it, that's fine. Just whenever we make a break today, just have a look. And I want to make sure that you guys know what to do and do it by Thursday, okay? Okay, let's now revisit cosmic velocities. Cosmic speed.
Oh yeah, and I won't be here Thursday because I have an interview.
Oh, well, what kind of interview?
For Cornell.
Oh, nice. Good luck.
Thank you.
And what would be your major?
Probably CS and like a mix of math and physics, like CS and engineering.
So is CS part of their engineering college, or
Yes,
is it
yeah,
part
it's
of
part of the
science?
College of Engineering. Yeah,
Yeah, it's like at Penn State.
yeah.
But math and physics is a separate college, College of Science. Hopefully you can do both. Okay, so let's revisit. Last time we talked about the first cosmic speed. Speed, as you remember, that was the minimum projectile velocity that makes it orbit the Earth without falling, so that it covers, like in 1 second, it covers precisely as much distance as it needs for the Earth's surface to recede by the amount it falls down. So in 1 second, objects fall by 5 meters. So we did some geometric consideration and found that you need to travel 8 kilometers so that the surface of the Earth goes down by 5 meters. Okay, and if you can do it in 1 second, you will never hit the ground. So that was a simplistic consideration, but let's do it a little bit more rigorously using Newton's laws. So here is the Earth, and here is the projectile that goes around with some velocity. So we know that this projectile is subject to force of gravity directed toward the center of the Earth. And I don't want to call it mg anymore. I'm just going to call it fg and use the more accurate Newton's formula, because we want to generalize it to some other planets. So we don't want to just stick to Earth's situation. Okay, and one more thing that we'll need here is the Earth radius. And of course the mass. So this is the Earth radius, and it has mass and Earth. We know these guys already. So what we can do, we just can apply Newton's second law to the projectile and write that F equals ma, right? Fg equals ma, and a is the centripetal acceleration. Okay, and then we expand it. We have g m Earth times little m over r Earth squared equals m v squared of r, right? You guys with me so far? So we're pretty much there. So now it's pretty straightforward. So we also cancel one factor of radius and obtain something that I'm going to put here. V1 equals square root of g m Earth or r Earth. Okay. Any questions about this? So if you do the math real quick, you'll find that this is pretty much the same thing in disguise. So this is numerically equal to 8 kilometers per second or 5 miles per second. But this is more general. So you can now go to any planet. You can go to the moon, put moon's mass, moon's radius, and moon's and gravitational constant, and you get the escape velocity. Sorry, the first cosmic speed for the moon. Or you can go to Jupiter or whatever and find the corresponding speed. So all you need to know is the mass of the planet or star and its radius. Okay. Now let's talk about the second cosmic speed, which is also known as the escape velocity. So as the name suggests, it's the minimum speed of the projectile to actually escape the planet. Okay. minimum projectile speed to escape the planet. Okay. Now, well, let's understand a couple important things. First off, which direction is the best to shoot the projectile at to make it more likely escape for a given fixed launch speed?
Straight up.
Radially, right?
Yeah.
Not like in this picture, but like straight along the radius. Let's just make sure we're on the same page here. So as the projectile moves to a larger and larger radius, the gravitational force gets weaker and weaker and weaker. So the idea is that if the gravitational force gets weaker fast enough, or if the projectile picks up radius fast enough for the gravitational force to decrease fast enough, it may actually escape. Make sense? Okay. So let's do that. So let's say where we're talking about the radial escape. And so I want to use the energy approach here. So we're going to consider UG versus radius graph. So you guys remember, it looks like upside down or negative hyperbola. Right? UG equals minus G M Earth M over R. UG. Folks, does that make sense? A quick way to check it: take derivative, the radial derivative, you get the gravitational force. Right? Force is a negative derivative of potential energy. Okay, now where are we here? We're sitting, let's say here, where little r equals Earth radius. This is where we're sitting. Where do we need to get? Well, we want to escape to infinity, right? We want to escape far away from the planet. Now, somewhere here. That immediately tells us how much energy we need for that. Right? We need this much kinetic energy, right? To climb up from this potential well. Am I saying clear words? Do you guys understand what I'm talking about? Okay, so this is the required kinetic energy. So what is it? K equals the magnitude of UG initial, because UG final is 0. Okay. So what is this? This is just this expression here. If you substitute the Earth radius. Okay. And this is equal, as you understand, 1/2 mv squared. Now compare this and this, cancel the little mass. You get that V equals square root of 2g m Earth over R. And this is exactly the second cosmic speed or the escape velocity. You guys have any questions? How we got here? All is good? Okay, so I want you to compare and contrast these two velocities.
Oh, is it double?
I wouldn't say double. It's actually a root of 2
Oh,
times.
root 2 times. Yeah.
Yeah. Kinetic energy would be double, but as far as speeds, you can write root 2 times. Okay, and that's not a coincidence. It's actually true for any planet or star. So again, intuitively, one might think, oh, yeah, you started orbiting the planet, but it's going to take much more to escape. No, not much more. You know, root 2 is roughly 1.41. So like 41% more speed and you're gone from the planet completely. Okay. There is also a third cosmic speed that I actually leave for you to compute at home. Who knows what that means? Third cosmic speed. What is that about? Yeah, you can say, I don't know. And I'll tell you. I'm just curious. So if you happen to know. So what's the next thing you want to try to escape from after you escape from Earth?
A black hole.
Oh, that's pretty ambitious. But we'll talk about it. We'll talk about it. Sun, yes, Joseph. The next thing to escape from is the solar system. Okay, so minimum projectile speed to escape the solar system. So technically, it's another escape velocity. So you should be able to use this formula down here. You have to be careful, right? Just make sure you find the right values for things here. So this I leave for you to do at home, okay? Bonus questions, do at home, and find out the necessary constants, okay? You can even check your work, like check your answer, but I want you to do the work, okay?
Just the sun, which is the most significant one.
Yes,
You need the sun's mass.
Yes, and yeah, we assume that you don't hit any other planet or anything on your way out. You only worry about the sun, but just still there is a subtlety that I don't want to tell you yet. I want you to figure it out yourself, okay? Let's actually go back here. As far as numerical value, this is approximately 11 kilometers per second or 7 miles per second. Okay, so if you can make 7 miles in 1 second, you actually escape from Earth. Or if you can throw, say, baseball this fast up, then it will likely escape from Earth. But yeah, let's talk about black holes. So first, tell me how much you know about black holes.
Not too much, but like I've heard of like Schwarzschild radii where you can orbit a black hole, and then like it has like a unique gravitational field somehow.
Well, you know some important names here. Okay, but first let's just understand that we understand black holes the same way. So the original idea behind black holes was an object that is so gravitationally strong that even light cannot escape it, and that's why we call it black hole, right? That doesn't shine. So the first attempt at actually, doing something about these objects was more than 200 years ago by Laplace, who you may know from math. Have you heard this name? Yeah, a famous French mathematician. And he did a little bit of physics too. So what he basically did in like 1795 was using Newtonian mechanics and what we just derived with you guys right here. He said, okay, let's look at this formula. Let's take a planet or a star and like fix the mass, but squeeze the radius. Don't do that at home. So if you decrease the radius, obviously the escape velocity will increase. How much can it increase? Well, in theory, if you are capable of squeezing the planet to an arbitrary size, you can make the escape velocity arbitrarily large. But the moment it exceeds the speed of light, that would imply that even light cannot escape from that object, right? And that's when you say, oh, you have a black hole that doesn't let anything out, even light, because light is the fastest thing. Obviously, nothing else can escape either. And how small do you need to squeeze it to? Well, it's easy to see, right? You just set v2 equals speed of light and solve for the radius.
Or you can just like set m over r as like some kind of density.
I wouldn't call it density.
Oh yeah, it's not that. Is there like a term for that?
There is a term for that. It escapes me now. It's not super commonly used, but there is a term. They use it in astrophysics to describe how close a stellar object is to a black hole. So basically, well, they don't actually, there are versions there. For me personally, it's more convenient to talk about the unitless parameter, such as 2gm divided by c squared. If that is equal to 1, that's precisely like black hole. And if it's less than 1, that means it's not yet black hole. Okay.
Why do they say that black holes have infinite density? Is that true?
It doesn't. No, it doesn't have infinite density. Well, we can talk about it. Let's just gradually get there. Okay. So let's set v2 equals speed of light, which is, as you know, 3 times 10 to the 8 meter per second. Okay, something in the chat. Let me check what you guys write. It has a large density, right? But it's not a point, and we'll talk about it. It's not a point. Today I was planning for some really brief overview of black holes, like scratching the surface. Didn't mean to go anywhere deep, but maybe some other time we can. When you gather more guys, we can talk about it. Again, singularity is something that was believed to be at the well, there were stages. I still want to do things gradually. So, of course, media does everything that you mentioned. So, let me introduce a bunch of terms here, and then we'll speak the same language, okay? So all these words certainly floating there: singularity, infinite density, all those things, but we need to be careful when we use them, okay? So if you do this and solve for the radius, then you get what was called gravitational radius. I'm not sure if Laplace himself called it gravitational radius, but this was the term. This was the term originally, and that is given by, if you do the math, you get 2gm over c squared. Now, m could be any mass of whatever object. Basically, this equation answers the question, to what radius do you need to squeeze an object of a given mass to turn it into a black hole? Make sense? The other two things in this formula are fundamental constants, gravitational constant and speed of light. So you don't really get to play with those, but you can play with the mass of the object. So if you grab different stars, they all will have different gravitational radii. For example, if you take Earth, okay, let's say m equals m Earth. Do you guys want to do a quick calculation and find Earth's gravitational radius? Oops, sorry, 6 times 10 to the 24th. And as you remember, G is 6.67 times 10 to the negative 11 meter cubed over kilogram second square. And speed of light is up here. So do you want to tell me? Oh, that was quick, thank you. And this looks correct to me. So I'll like round it up and say 0.01 meter, which is 1 centimeter. So you guys imagine how small it is. 1 centimeter, like there are 2.5 centimeters in an inch. So 1 centimeter is roughly this. So this is the radius. Diameter is twice as much, a little bit less than an inch. Okay. This is Earth-sized black hole. You can fit it in your pocket. Okay, just don't do that at home. Just curious, have you guys seen the TV? I probably ask you, Stargate TV show. Like, first there was a movie with Kurt Russell, and then they made a series out of it, which ran for more than 10 years, from 1995 till like at least 2005, maybe later. No, that's an interesting movie to watch.
I saw it.
What's that?
I've seen it, but I've never watched it. Like I've seen the banners and stuff.
Okay. So neither the movie nor the series. Well, I actually recommend it. So if you if you consider us to watch, at least the first few seasons, they try to stay scientifically consistent. So they had this idea of stargates, which would initiate a wormhole between different planets and galaxies, and you could travel through them. So they had their like, restrictions.
Wormhole?
What's that?
What even is a wormhole?
A wormhole.
Is it different? How different is it from a black hole? Is it?
Oh, it's very different. So imagine that space-time is curved, which it is, right? And the idea is that the wormhole is a path that would connect two otherwise very distant parts of space. So let's say if you were to travel to, so what's on the opposite? Let's say China, right? If you were to travel to China using regular means, you would like travel around the Earth. But if you could cut through, that would save you some distance. Not a lot, right?
So it's like creasing paper, right? That's the analogy I usually see.
Yeah, if you fold paper and instead of going within the surface of the paper, you cut through.
Go through, yeah. Yep,
yeah. Of course, that requires a lot of energy to alter the space-time structure, but according to the movie, there was some ancient civilization that had built those stargates. All you need to do is to dial the right code to the right planet, and it creates a wormhole to that, and you can travel. So eventually they encountered a very advanced evil alien species that was capable of squeezing planets into black holes. So that's why I'm saying this. So they somehow had the technology to create black holes out.
Black holes and wormholes anywhere related?
Black holes. So that was a very aggressive alien civilization. They they killed planets by turning them into
Oh
black.
no, like does a black hole have a wormhole in it? Or
Mm,
is that unsure?
well, okay, here is the thing. There are a few different types of black holes. Some of them may be acting as wormholes to other universes, to other universes. So if you get sucked into that type of black hole, you may actually get out in some other universe. Okay, but that's not the standard black hole that Alvin mentioned. That was the simplest one. So let me just tell you a few things here. You know what? I think I'll just share some slide with you that summarizes the history of black holes. And I'll take it from there. And like I said, I'll be happy to have a totally separate class on this, but maybe after we started prepping for F equals ma, because that material is not included, as you can guess, but something about general relativity may show up. Well, I wouldn't say USAFO, but IFO maybe. So that's not our top priority. I know it's fun and we can totally talk about it, but not immediately, okay? So for now, I'll just have this little overview. So like I mentioned, Laplace back in the 1795 did what we just did using Newtonian mechanics and got this value for the gravitational radius. And then comes Maxwell. Well, and you know Maxwell, that is like the second half of the 19th century. 1865 is when he published his famous Tractatus on electricity and magnetism. So light is a wave, and we know that Newtonian mechanics doesn't really describe light. So it's not correct to say that whatever the calculation Laplace did using Newtonian mechanics, it's not correct to say that it actually, applies to light. So, however tempting that approach means or feels, how do you know? How do you know that light won't really escape what you call a black hole? So, and then comes Einstein, 1905. You probably know the paper that he was actually awarded Nobel Prize for. That is not the paper on relativity, that's some other paper. Do you guys know what that is?
Was it on field equations?
Well, they don't award Nobel Prize for some equations. So that was for his explanation of the photoelectric effect. Does that ring a bell? So, for example, photoelectric effect is responsible for a lot of things today. In particular, all those light diodes. Like when you approach a door, an automatic door, that's based on that. Or like whenever elevator door stops from closing, that's also based on that. But of course, back then it wasn't existent, but they did know the effect. So Einstein got his Nobel Prize for explaining the photoelectric effect. And part of the explanation was that light was treated as a particle, photon, right? Einstein tossed the term photon. So now light as a particle can kind of be described by Newtonian mechanics. But then it's a massless particle. Photons are massless, and Newton came up with his law that only worked on massive particles, right? There are explicitly two masses in that equation for force. If one particle is massless, there is no gravitational force on it. Okay, it seems to be a problem. And then Einstein comes again in 1915 with his general theory of relativity, where he says that force of gravity is not really a force, the way we understand it, it's a feature of space-time. It's curvature of space-time. So our space-time is curved, and everything within it has to comply that curvature, including light. So what black hole does, you may have seen those two-dimensional versions or two-dimensional pictures that, you know, with a funnel.
Light cones.
Yes. So black holes, or any massive object for that matter, bends space-time, curves space-time. So things have to follow curved trajectories. So light that travels along the shortest path, geodesics, geodesics becomes curved, okay? And light has to follow those, and those curves become closed.
Like Fermat's theory of light, like the refraction thing, or is that a different thing?
They're pretty much, yes. Pretty much. You can't
How did they
argue
figure
along
that
those
out?
lines.
Did
How
they
did
just
they
guess
figure-
that it always goes through the shortest or the longest path?
Well, let me tell you this much. In theoretical physics, like after you learn Lagrangian mechanics, and I understand some of you guys heard about it, because some of you tried to use Euler-Lagrange equation the other month. So the most fundamental way to state like equations governing a particular physical system is to write a functional called action. Okay, and then you use the least action principle on that, in the sense of doing variations of that. And then all you need to do, if you want to describe whatever physical system, all you need to do is to come up with the right action. So once you got the action, the rest is math. Okay, so this stems from the Fermat principle. So the person who actually first stated the least action principle was the Scottish mathematician and physicist Hamilton. Like Hamilton's equations, if you know the symbol nabla, that's also his brainchild. So it's not how they know, it's a way of stating things. Like you have to have some fundamental principles, and this is the principle, least action principle. I hope that answers some of your questions. Okay, so this is something that this is the name that Alvin mentioned earlier today, Schwarzschild, a German physicist or astrophysicist. So let me tell you a little story here, which is pretty sad though. So Einstein published his general theory of relativity in 1915, and he published what we now call Einstein's equations, like beautiful equations describing interaction of gravity and matter. And by matter, we call everything else other than gravity. That includes electromagnetic radiation, that we also call matter in general theory of relativity. Beautiful equations, but they're very complicated equations. Again, I'm going to say all these words and you tell me if they make sense. These are 10 coupled nonlinear partial differential equations. Does that ring any bell?
I heard PDE in there, and I heard those are hard.
PDE, yes. PDE is one thing, but then you heard the word 10, right? There are 10 equations coupled. That means, like, say if you have algebraic equation, 2 equations, that means you cannot solve them independently, right? They're a system of equations. So variables show up in all equations. They're all mixed up. And the worst word there is nonlinear, because you can learn regular methods of solving linear equations. And that's what you'll do whenever you take like a PDE course. But nonlinear equations, there are no regular methods of solving them. They either have to be very special so that there is some smart idea how to solve this particular nonlinear equation, or you have to solve them numerically. Okay, there is no like analytic approach to that. So Einstein thought that nobody would be able to solve his equation anytime soon, even in the simplest situations. However, he was wrong. Just a few months later, this guy Schwarzschild was able to solve Einstein's equations in this spherically symmetric static case. Static means time independent, like same over time. Okay, and that's what we call spherical black hole or Schwarzschild black hole. Okay,
What's a non-spherical?
What's that?
What's a non-spherical black hole?
Well, non-spherical, not spherically symmetric. That's a rotating black hole.
Oh, it like bulges.
Rotating. Okay. So I can tell you the timeline a little bit later. So let me just to give you the name to look for Kerr, Kerr, a New Zealand mathematician. Kerr. I think he's still alive. He's still alive, or he was a few years ago. So the sad part of the story is that Schwarzschild, he was in his 40s when he did this. He was a pretty established astrophysicist in some pretty good German university, but he volunteered in the First World War, and he was wounded. So he derived this while wounded in the hospital, and he died soon after. So this was the last thing he did. Ironically, we don't remember anything else he did, even though he did quite a few things by then. This is the main thing that we attach his name to, Schwarzschild radius. That's how we call it, and Schwarzschild black hole, and so on. Now, remarkably, and that's one of the most amazing things about this, is that he applied general relativity, Einstein's equations, and he got exactly the same answer that Laplace did, using the wrong theory, Newtonian mechanics. He used the wrong theory, got somehow the right answer. Okay. Now, the funny thing about this is that the term black hole was tossed much later, 1967. And that was done by an American physicist, John Wheeler. You may have heard of him. He had a lot of students who got the Nobel Prize in physics before him. One of them was Richard Feynman. Another one is Kip Thorne. Does this name sound familiar? Yeah, Kip Thorne actually just got Nobel Prize like a couple of years back for LIGO. And he's the guy who did the equations for Interstellar. Okay, yeah, so Einstein died in 1955. Well, he did not use the term black hole. So black hole was much later. I actually honestly don't know what Einstein called it, but he did not call it black hole. Okay, now after this, people tried, solving some more complicated versions of black holes. And a couple years later, they were able to find the solution for a charged spherically symmetric black hole. That's not too hard to put a charge, although we have not really observed any charged black holes, but theoretically it's fun to think about. So it took another 50 years till 1965 for people to be able to describe this rotational black hole. It's really hard, really complicated equation. So what happened is that this Kerr guy in New Zealand, he was a mathematician, and he never even thought about black holes. But he was doing something, and he had a physics friend who looked at his metric, that the way space-time is described is using metric tensor. Roughly, it's this thing that tells you how to measure distances at different points of space. Okay. So he looked at that metric and said, "Oh, it looks like it may be a solution for spheric for rotating space-time, rotating space hole, black hole." And it's obviously much easier to check if a certain function is a solution of equations than to find solutions, right? You can give it like a 5-year-old a solution and ask, does this solve a quadratic equation? And they would be able to check by plugging and chugging, right? Even though they may have no idea about how to solve quadratic equations. So they did, and amazingly, it was indeed describing a rotating black hole. That's why it's called the Kerr black hole. But Kerr was not really looking to find that solution. So he did something very different. And then soon after, they did the charged rotating black hole. Again, putting charge on top of non-charged black hole is not that hard. So this is a brief overview of different types of black holes and Abhijit. So some of them may be leading to wormholes to other universes. The usual approach to describe the space-time structure near black holes is using so-called Penrose diagrams. So Penrose is this year's Nobel Prize winner. I'm not sure if we already discussed this guy with you guys, but this is a British physicist that you may know. He was in the thesis committee of Stephen Hawking. Do you guys know who I'm talking about? Roger Penrose? Yeah.
I've definitely heard his name before.
But we did discuss it with you, did we? Yeah, so have you seen the movie about Stephen Hawking, The Theory of Everything? So Roger Penrose, the actor playing young Roger Penrose is in the movie. He shows up in the movie a few times. But the actual Roger Penrose is almost 90 years old now. I'm proud to say that he was a part-time Penn State professor. When I was at the main campus, he would visit twice a year for a couple of weeks. And I have a few books signed by him.
He's a mathematician.
He is a mathematician, but he did quite a few things in differential geometry and general relativity. So the main results that Hawking obtained, like those famous theorems, they were done together with Penrose. They call like Hawking-Penrose theorems. They basically prove that black holes are a feature, not a bug. So they're not just some unique exotic solutions. They must exist. And this is a natural consequence of general theory of relativity under very general conditions. Okay, I think we kind of got distracted a little bit. So why don't we take a break and then we'll start talking about planetary motion. So 10-minute break. Okay, so let's talk about Kepler's laws now. So it also has an interesting story to it. So technically, to be rigorous, they should not be called laws anymore, because in physics, what we usually call law is something that we cannot prove, something that just, an observation about what nature does, like, Newton's universal law of gravitation. Right? There is no, well, at least at this level, there is no more fundamental way of thinking about gravity. So just to, the way it works, the way it is. So Kepler's laws were laws because Kepler, as you know, lived before Newton. But after Newton's laws of gravitation and Newton's law of motion, he was able to actually prove Kepler's law. So you should really call it like Kepler's theorem, because it's a consequence of some other more fundamental things. Another interesting thing about Kepler's laws is that it took Kepler probably 25 years to get it right. So he had like 2 unsuccessful attempts to get it, and then on the 3rd attempt he made it. Attempts at what? So he had a lot of astronomical data that he inherited from his teacher Tycho Brahe, a Danish astronomer that you may have heard about. So he had this tons of astronomical data, and he tried to make sense out of it. He tried to find some simple patterns behind the planetary motion. He was certainly aware of Copernicus's idea that, you know, a good reference frame is heliocentric. That's when math becomes particularly simple. So he made 3 statements, but again, that was the 3rd successful attempt. Let me just remark on one unsuccessful attempt that he had. So back then, let me remind you, people knew only 5 planets. So up to Jupiter. So and what's interesting is that the orbital radii were roughly doubling. So he had this geometric analogy with perfect solids. Do you guys know what perfect solids are? These are polyhedra with identical faces, edges, and so there are only 5. It cannot be more than 5. So the simplest one is tetrahedron. Then you have cube, octahedron, and then 2 larger ones, icosahedron and dodecahedron. So that's it. And Kepler made this analogy between planets and those polyhedra, he said, they're like inscribed in one another. That was a beautiful theory. Everyone liked it. But first, it was wrong. And second, it broke down completely when they discovered Saturn, because the 6th planet didn't fit that picture with perfect solids. So anyhow, let's. I'm going to first state the laws, and then we'll see how we can prove them. I think today, but hopefully get a good idea about it. So first, the first law is that planets follow elliptical orbits around the sun. Orbits around the sun. So what is an ellipse? Ellipse is a squished circle, right? To say simply. Does anybody know how it's defined mathematically?
A locus of points that have the same sum of distances from 2 points.
Exactly. Exactly. Yes. Guys, did you catch it, or did you know that as well? Joseph, Abjad? Good. So, and those 2 points are called foci, right? There are 2 foci, one on the left and one on the right. You can call it F1, and this is F2. So exactly as Alvin said, if you pick a random point on the ellipse, then these 2 distances add up to a fixed value. Okay? So
Eccentricity of the orbit for around the sun is like really close to a circle, right?
eccentricity is very small for most of the planets, including the Earth. The largest one was for what used to be a planet, so that has a particularly significant eccentricity. But Earth, Mars, Venus, they have like negligible eccentricity. Their orbits are almost circular. So that has to do with the focal distance, right? The distance between the F1 and F2. You imagine if you squeeze them together into one point, then this definition becomes the definition of a circle, right? where you just have a constant distance to a given point. So let's call it R1, R2. So mathematical definition is that R1 plus R2 is constant. And folks, is it obvious that this sum equals this distance, the longer dimension of the ellipse? Is it obvious, or do you want me to elaborate?
Yeah, it is.
Okay. Okay. So usually that is denoted by 2a, where a is the kind of the longer radius, so to speak. So a is called semi-major axis. There is also semi-minor axis, but that's not as significant. It doesn't show up in those equations that we'll get. Semi-minor axis. This is the smaller radius. So this is 2b. Now, importantly, where is the sun in this picture?
Either foci.
Exactly. So importantly, again, it's not very intuitive for people when they see the first time. They tend to say that sun is located at the center of the ellipse. No, it's located at the focus, either the left focus or the right focus. Let's say here. Okay, so this is the first Kepler's law that says that planets follow elliptical orbits where the sun and the sun is at one of the foci. The second law is stating that the sectorial speed is constant. Does that ring a bell, or do you want me to define this thing?
Like it sweeps out equal areas and equal times.
Exactly. So so it's clear that since this is not a circle, general planet would not follow a uniform circular motion. So it actually may speed up and slow down. And in fact, you can use whatever knowledge you already have to argue where the planet moves the fastest, where it moves the slowest. So do you want to say anything about it?
Yes, so it would obviously go faster when it's near the sun, and that's why the area over there is small, which is why it sweeps it faster.
Right, so this explains this, but is it clear why? So let me introduce a couple of terms that you probably know. This is called perihelion. Does that ring a bell? Which means closest to the sun. You know, helion, helios stands for the sun, and peri means closest. And this like there is another Greek word apo. I would like you would say apohelion, but the letters merge together. Yeah, the letters merge together so that the word becomes aphelion. But if you talk about the Earth, for example, you would say perigea and apogea. Geo stands for Earth, as you know. Okay, so well, let's put it down. V equals max at perihelion, and it equals mean in at aphelion. Okay, but can you argue why it's true, like based on the physics we've learned so far?
You can use conservation of energy.
Okay, did you want to say a couple more words here?
Okay, so we can assume the mechanical energy is always constant, more or less constant, right? So it's equal to the potential energy from the sun plus its kinetic energy.
Planet's kinetic energy, yep.
when it's near the sun, the potential energy is lower, so the kinetic energy is higher, and vice versa.
Very good. Makes sense to everybody? Okay, yes, exactly. This is the reason. And then, as Abhijit said, that explains why Kepler even like observed that. So if you pick a random point, here and give planet some time delta t, you may find it somewhere here. So you can say this is delta t along the orbit. But if you look at the planet somewhere here, it moves relatively slowly. So if you give it the same amount of time delta t, you'll find it not too far away. So same amount of time, different arc length covered. But if you shade the sectorial area, oops, not this one. So you need to do this. Yeah, so if you consider this narrow, long triangle or sector, this area is actually equal to this area. So if you call this delta A1 and this delta A2, then they're equal. Or Kepler would write it like this. He would write that the time rate, or the rate at which the area is being swept, is constant. So this is second Kepler's law. And the third one says that the orbital period squared is proportional to a cubed. A is the semi-major axis. That's why I said it's important, because this is the semi-axis that shows up in the equation. And again, folks, he just came up with this based on data. He didn't really put any physics behind it. And physics did not exist then, so it only started existing with Newton. Okay, so now let's see why these things are true. So it's actually the hardest to prove the first law. So let me tell you, a priori, it's not even obvious that the orbit should be planar curve. Like, why wouldn't it be something in 3D, wrapping around in some random manner? Why wouldn't it be true? Okay, so this will prove. Okay, I'm going to prove that the orbit is planar. That is within one plane. And we're going to use conservation of angular momentum. Okay. So last week, we introduced the concept of angular momentum for a point particle. So we're certainly going to treat the planet orbiting the sun as a point particle. Sun is fixing the axis of rotation. So we can say that this is R cross P, right? R is the radius vector. Changes over time, P changes over time, but their cross product stays constant. Okay, and we're going to use both aspects of angular momentum, magnitude and direction. First, direction. So of course we know that the cross product is perpendicular to both things. So L is perpendicular to the radius vector, and it's perpendicular to the planet's momentum, right? And of course velocity as a result. So let's say there is sun somewhere here, and then there is a planet somewhere here, and you kick it with some momentum, P initial, this way. So what do we have then? So this is the initial radius vector. Which way is the angular momentum of the planet initial? Which way is it pointing?
Out of this screen.
Okay, you guys use right-hand rule, right? So it's out of the page, and the direction is constant. Okay, that means it stays out of the page. Okay, now what does that mean for us? That means that R and P have to stay perpendicular to L, right? So now, as R has to be perpendicular to L and P has to be perpendicular to L, both of them are within the plane. Okay, that's almost proving it. So what does P do? P is mv. V tells you which direction the radius vector will change next moment. So next moment, the planet moves somewhere here. It gets a new radius vector that's still within the plane. So if it's still within the plane, that means P has to be within the plane. Okay. So, and the thing repeats. If P is within the plane, that means V is within the plane, and the next change in R is also within the plane. So R always stays in the plane, and through this, it implies that P stays within the plane. Okay? So the whole trajectory has to be within that plane. So we just proved that the trajectory is planar. This is based on the constancy of direction of angular momentum. Okay, now it's not obvious that this trajectory has to be closed. Okay, that we won't prove today. We'll maybe try to prove it on Thursday. Okay, that's pretty advanced stuff. Okay, that will deal with differential equation. So again, let me just state non-obvious statement is that the trajectory is closed. And in fact, you may know that Mercury's trajectory is not closed, to be rigorous, right? It's not precisely governed by Newton's laws. You have to use general relativity for that. So basically, what's important is that we will be assuming that the only force acting on the planet is the force of gravity, Newtonian gravity, which is toward the sun and inversely proportional to the distance squared. So if you imagine that, oh, how do we know that angular momentum is conserved? I didn't prove it. I should have. So let's prove that. Prove that L is constant. Any ideas how to prove it?
You can start from conservation of linear momentum.
Is it conserved though?
Oh,
It's certainly not conserved, right? That it rotates, so, and it speeds up and slows down. So linear momentum is far from conserving here. But if you recall that the time derivative of angular momentum is the torque, and the only torque that can possibly be here is that by gravity, right? Now, what is it? This is R cross FG. And what is this cross product?
0.
0, right? Because radius vector is anti-parallel to G. So they make an angle of 180 degrees, and you know cross product of such angles vectors is 0. Okay, that proves that angular momentum is indeed conserved. Okay, and we can argue the above. Such forces that always act towards a fixed body or always away from a fixed body are called central forces. So electrostatic force, for example, is also a central force. And a lot of things that we're going to prove here will apply to electrostatics. Okay, so Fg is called central force. So one important consequence of that is exactly that they don't affect the angular momentum. They create no torque. Okay. Okay, now let's come back to this. Trajectory is closed. This is not obvious. And it turns out that even for central forces, it's not obvious. Central force could be, let's say, it's inversely proportional to some, not necessarily inversely. Let's say it only depends on radius, okay? And it depends on radius as a polynomial, some power n. So it turns out that there are only two values of n for which the trajectory is closed. So trajectory is closed for either n equal -2, as you can guess, right? That's Newton's law of gravitation. And there is one more value of n for which it works. You happen to know that? No? Okay, I'll tell you. N equal 1. So that's basically Hooke's law in disguise. If force is proportional to distance, right? That's like spring. It also yields closed trajectory. So think about, like, it could be a two-dimensional setup, set it in a box and have like two sets of springs along one dimension and along the other one, and like have 4 springs and put a ball in the middle. Does that make sense? And then you can like kick the ball or stretch it, deflect it in any direction, kick it in any direction. It will make an elliptical orbit. Maybe not necessarily elliptical. No, I take it back. It would be the Lissajous figures, but they will be closed. They will be closed. Okay, only two possible ends. So remarkably, one of those ends is from Newton's law of gravitation. If you had, say, n cubed, r cubed in the denominator, that wouldn't be closed. And in fact, that's exactly what happens when you start accounting for general relativistic effects, especially near the sun, where they're the strongest. That's why Mercury is the most affected. So Mercury has not precisely Newton's law of gravitation to obey, but there is a little correction that looks like 1 over r cubed. And that correction makes the trajectory not closed. Why? That's why you can visualize Mercury's orbit as an ellipse, but that slowly rotates, whose semi-major axis is rotating over time. And that was well studied before Einstein. So Einstein, it was one of the things that Einstein used to check general theory of relativity. Okay, so this is the first law. The second law is fairly easy to prove. So you need to use the constancy of the magnitude of angular momentum. So use the fact that this is constant. So this is what? R times P times sine theta, where theta is the angle between the radius vector and momentum. I leave it for you folks to prove that this is proportional to the sectorial speed. So this is what you need to demonstrate. Does that make sense, folks? So massage this expression and show that this is proportional to the sectorial speed. Okay, and then that will prove that sectorial speed must be constant. Okay, now third law, we'll prove, for now, we'll just prove it for circular orbits. We're not ready to do elliptical yet. So prove for circular orbits. So imagine that, yeah, it works pretty well for Earth, for example. So let's say we have the sun here. And this is the Earth that orbits the sun with radius. We pretty much already proved it. And by the way, this is the astronomical symbol for the sun, the dot in the circle. So we basically proved it a few slides back. If you look at this derivation, Newton's second law, equating the force and the centripetal force, like force of gravity to the centripetal force, you can get it. So let me just copy this. Okay. We have gm of the sun times the mass of the Earth over r squared equals m Earth times v squared over r. So you see that the mass of the Earth cancels as before. I won't cancel the radius. So what I want to do instead, I want to express v in terms of the period, the orbital period. So I'm going to take the circumference, just 2 pi r over t. Make sense? Circumference over period gives us the speed. So I'm going to plug it in here. Just carefully massage. So gm sun over r squared equals 2 pi r squared over r over t squared. Does that make sense? Just square this whole thing, and then let's collect t on the left hand side and everything else on the right hand side. So we have t squared equals. Now, what power of r will have? Technically, there is r squared here, but we cancel one r. Okay, it becomes r, and then times r squared from here, that becomes r cubed. So you already see that this works, right? So we need t squared to be proportional to a cubed, and a equals r for a circle, obviously. Now, what is the rest of the equation? Let's carefully collect that. So we have 2 pi squared, which gives us 4 pi squared over gm of the sun. Okay. In some literature, this combo in front of r cubed is called the Kepler constant. Kepler's constant. Again, Kepler had no idea what this constant, like where this constant comes from. He just had a numerical value for it based on the data fitting. But Newton actually explained not just why t squared is proportional to r cubed, but also figured out this constant in terms of the other, known things. Okay. Let's do quick exercise. So let's say the planet's orbital radius doubles. Say r2 equals 2r1. And you have the same star, same sun, the same star. What is the period ratio?
R2 over R1 to the 3/2.
Yeah, this is the scaling technique, and this is basically a 2, right? 2 to 3/2, or 2 root of 2, which is 2.8, right? Joseph, Abhijit, you okay with this? Yeah. So all you need to know is this the power here. You don't worry about the constants. They cancel out when you take the ratio. And the period, of course, we call a year. So if you want to say, find like how long is the year on Jupiter, you can just understand how far it is, plug that ratio into this formula with Earth, and you'll see how much longer the period is, the year is at Jupiter. Okay. So, so we're out of time, but tell me for Thursday, we could try proving the 2 things that we haven't proved. We haven't proved that the orbit is elliptical, right? So we only proved it's a closed planar curve, but we haven't proved it's an ellipse. So we can prove that. And with that, we can prove that, third law holds if you replace the radius with the semi-major axis. So guys, are you feeling interested in that? That will require dealing with some differential equations. You okay with that?
Yeah.
Differential equations plus polar coordinates will work in polar coordinates. If you're comfortable with those, then we can certainly do it on Thursday. Okay, that's the plan then. Have any questions? No?